finding derivatives when we have things multiplied together or divided by each other, right? Okay. So we did a little review on how to find derivatives using the power rule and things like that. Then we talked about this thing called the power rule, which I told you you had to memorize. And this rule kind of dealt with whenever we had things that were multiplied together and how to find the derivative of that, right? So essentially, if I can find my pen, that would be very nice. Okay. Essentially, if we have two things, let me see if I can connect my pen real quick. Okay. If we have, what is going on here? Oh, there we go. Let's see if this works. Okay. Maybe it's the wrong pencil. This is very sad. There we go. Let's see if this works. There we go. Okay, so essentially, if we have f and g, two functions multiplied together, the derivative of that is, well, the first times the derivative of the second plus the second times the derivative of the first. We did a few examples of this, and we realized that, okay, sometimes we have the option of using the product rule or not using it, but most of the times we didn't have the option, right? We have to use this rule, especially in examples like 7 or 8. How confident do you feel on doing example 9? Okay, I'm seeing, I feel pretty confident. I'm gonna give you a few minutes to work on this and then we'll work on this together. I think everyone's doing a pretty good job, but I do want to talk about some things, okay? Okay. Before I even start the question, I want to talk about kind of an approach for this. I got a good question as I've been walking around, and someone asked, okay, can I just like distribute? Whenever you see something times a polynomial, you can distribute things out, right? Okay. Well, you don't have to write this down because I'm going to show you why this might not be the best method. But we'd have 5x squared 7 to the x plus 2x 7 to the x plus 7 to the x. Okay. Why is that not really the best option?
Yeah, you're still doing a product 3 times.
Yeah, you'd have to do the product rule here, and you'd have to do the product rule there, right? Maybe it's easier for us to do the product rule 1 time instead of doing it twice, okay? Of course, you can do this. I wouldn't take off points if you did it, but it will take you a little bit longer, okay? So maybe we shouldn't do this, okay? Let's just figure out how to use the product rule as a reminder, okay? It doesn't really matter which one I choose to be f and which one I choose to be g, okay? Let me just do the first one as f and the second one as g. I think that's normally what people do, okay? Now, just as a reminder, the product rule says fg prime is f times g prime plus g times f prime, okay? Okay, using this rule, it says leave f alone. So I'll do that. 5x squared plus 2x plus 1. And it says take that and multiply it by the derivative of g prime. What's the derivative of g?
7x minus 1. So the power of x minus 1.
Not quite. There's actually, it's not the power rule. It's something else. There's actually a rule we had to memorize for exponentials. Will?
Log natural 7. 7.
Good, right? This one was one of those ones that we had to memorize. But the derivative of anything to the x is the natural log of that something times that something to the x. Okay. We're going to add on g times, okay, now we're going to do the power rule to find the derivative of f. Okay, what's the derivative of 5x squared? 10x. What's the derivative of 2x? 2. And what's the derivative of 1? 0. So I'm not going to write that down. Okay. So essentially what I did here is this is F, this is G prime, this is G, and this is F prime. Okay. So now I'm not really gonna clean this up. I guess one thing I can do, and we'll deal with this later. This is a little bit messy, so I'm gonna put the ln7 up front times 7bx, 5x squared plus 2x plus 1 plus 7 to the x times 10x plus 2. Okay, if you want to FOIL this out, you can. I would say for right now, I would be fine leaving it as this. Okay, now in the future, when we start applying derivatives, you might need to start simplifying things, but for now, let's just keep it as it is. Okay, any questions on example 9? All right. So we talked about when we have a product, let's talk about quotients. So when we have division, okay? So there is a way to derive this. I'm not going to do it in class because it takes a while. But if we have differential functions, we can divide them, right? Now here's the quotient rule. It's a little bit more convoluted than the product rule, but it's telling us to take the bottom, multiply it by the derivative of the top, subtract the top times the derivative of the bottom, and put it over the bottom squared. Okay, now I don't really like this notation because it's very lengthy. Most people write this. F over G prime is G F prime minus F G prime over G squared. Okay, this is something you also have to memorize. Okay, and the way I like to talk about this is instead of using G, I'll use the word bottom. So like bottom times derivative of top time minus the top times the derivative of the bottom over the bottom squared. Okay, that's kind of how I like to talk about this. Okay, let's try to apply this into an example here. Okay, so we have this this division here. Definitely looks like something that we can use the product on because we have two functions over each other. But I'm going to tell you, you can actually solve this without using the quotient rule and with using the quotient rule. Let's see how we can do it without, okay? Any ideas on how to not use the quotient rule for this one? You can, yeah. And oh, you're saying do this. X squared minus x minus 2. Oh, sorry, plus x minus 2.
Just put it in the numerator, make it x to the negative 1 power.
Yeah, like that.
Oh, yeah, sorry.
Oh yeah, you're good. And then use the product rule.
Yeah.
That's something we can do. Totally good. So then product. That actually wasn't where I was going with this, but that's a very good way to do that. Any other observations that we can do? Troy?
Maybe like 3 separate fractions.
Yeah,
X squared over X, X over X.
good. So Troy said, let's take the x squared, put it over x, the x and put it over x, and a 2 and put it over x. Okay. Drew's way is totally fine. Good job. But I think this one might be a little bit easier. So x squared over x is just x, right? X over x is 1. And we've got 2 over x. What's 1 over x? That's x to the negative 1, right? Okay, so we can continue doing that. Okay. Now we have written our y function in a pretty easier way to take the derivative. Let's find y prime. Okay. Well, we can just take the derivative of the individual pieces. What's the derivative of x? 1, good. What's the derivative of 1? 0. And what's the derivative of negative 2x to the negative 1? Good. Good. Okay, now if you want to see this a little bit slower, you took the negative 2, okay, brought the 1 over, so it's negative 1, and subtracted 1 from negative 1 to get negative 2. Okay, using the power rule as well. So this becomes 1 minus, or 1 plus 2x to the negative 2. What's another way to write x to the negative 2?
2 over x squared.
Great. This becomes 1 plus 2 over x squared. Okay. So this will be fine. You can combine the fractions if you would like, but this is fine for me. Any questions on finding this without the quotient? Good. All right. Let's find it with the quotient rule. So I'm actually gonna just write the equation up top here so I don't have to go back. It's x squared plus x minus 2 over x. Okay. And maybe as a reminder, I should write the quotient rule. So f over g prime is, gosh, g f prime, I'm not very good at this, minus f g prime over g squared. Good. Okay. Doesn't matter which one is f and which one is g now.
Yes.
Yes, right. F is the top, G is the bottom. You can't swap them up, okay? So make sure this one is F and make sure the bottom one is G. Okay, so why don't we just piece this together? G by itself is X, okay? F prime, what is F prime? 2x plus 1, good. Okay, so that was G, that's F prime. F is x squared plus x minus 2. What's g prime? 1, good. So that one was f, that one's g prime. And this is all over g squared. G is x, so we just have to square. Okay. So at this point, this would be okay. Since we have polynomials, let's just kind of clean it up just so it looks a little bit nicer and we can compare it to part A. I guess I can FOIL, right? So we're left with 2x squared plus x. And I can FOIL this negative sign over minus x squared minus x plus 2 over x squared. Okay. Looks like we're left with 2x squared minus x squared is just x squared. We have a plus and minus x that cancel each other out, and we're left with a 2 over x squared. Okay. And of course, if you wanted to split up the fractions, you'd be left with 1 plus 2 over x squared, which is what we got in part A. Okay. For now, I am totally fine with you leaving the answer like this. Okay. That's fine for me. A little bit later, we might have to start simplifying things though. Any questions on part B? All right. Why don't I give you some time to work on example 11? Nice job as I've been walking around. All right, so example 11, we had 2 of these guys here. We had a top and a bottom. Okay, so quotient rule might be a good way to go here. Mason, do you kind of want to take us through your steps here?
So first we follow the quotient rule. Yeah. Where plug in the top for property. That's and everything for derivatives.
Yep. And for now, this is fine. Okay, if you want to FOIL things out, that's fine with me. But for now, I'd say leave it like this. Pretty easy for calc professors to grade when it's left like this. If you want to FOIL it out, it's good practice anyway. Okay. Any questions on example 11? Let's go to example number 12. Okay. This one is written in a weird way, but it's essentially asking us to find the derivative, right? The displacement is this function. The velocity is always the derivative, right? So whenever you're asking for velocity, we're asking for the derivative. Okay. Who wrote this one up? Jude, do you kind of want to take us through your steps here?
Yeah. So the first part, I put g, which is 1 plus x squared times by the derivative e to x, which is e to the x, minus e to x derivative of the bottom g, which is 2x, divided by 1 plus x squared
Perfect. Yeah, perfect. It's actually pretty nice that you noticed that all of them had an e to the x and you foiled that or factored that out. I would be fine with this answer for now. This is also a good answer as well. Any questions on example 12? All right. The last thing we're going to do today is we're going to talk about a different example. Okay. Example number 13. Okay. Any suggestions on how to do this one? Troy? Oh, okay. So yeah, you could use the quotient rule, but if the bottom is 1, the quotient rule actually doesn't really help that much. Any other suggestions on how to solve this one?
I mean, you could just say the prime of it is 3 times, like with thing in parentheses, x plus 2, and just that's squared.
Okay, yeah, so you're like, okay, I know that there's something being cubed, and maybe I can use the power rule using that way, right? Sam?
Zach was right, but you gotta include the derivative that's inside the parentheses.
Okay, so we're moving towards something that you might have seen before, right? Which is called the chain rule. Okay. Without the chain rule, is there any other way we could do this?
Factor it out.
Yeah, we could factor it out, right? So that's something that we're used to doing. But that takes a while, right? You do x plus 2, x plus 2, x plus 2. Okay, now I'm going to save you the work here, but this would turn into x cubed plus 6x squared plus 12x plus 8. Okay. And the derivative of this would be, well, 3x squared plus 12x plus 12. Okay. So yes, we can factor things out. But what if this was the power to like the 7th power or the 10th power or the 15th power? Would you want to factor that one out? No, I don't even want to factor this one out. So let's see if there's like an easier way to do this. Okay. Rather than consider this as like one function, I actually want to introduce something that turns this into maybe 2 functions. Okay. And the way I'm going to do this is by introducing a substitution. Okay, and the way I'm going to do this is I'm going to make up a new function that looks very similar to this one and see if I can take the derivative of that. Okay, so I'm going to make a function y, and I want y to be the same as x plus 2 cubed. Okay, so I want y to be x plus 2 cubed. Okay, so I'll do that. And I think as Zach said, there's something being cubed here. Okay, what is that something being cubed? X plus 2. X plus 2 is the thing on the inside. I'm going to call that u, just because, well, I felt like it. Okay. I'm going to call u the inside function. Okay, so that's how I'm going to refer to this. Okay, and u is just a label for the thing on the inside. Now, if I look at y, x plus 2 cubed is the same as u cubed, right? Okay, so I just rewrote my function in terms of an inside function being cubed. Okay, so well, we have 2 functions, and each of these are a little bit easier to take the derivative of, right? Okay, let's do this. I'm going to ask you a few questions. This means take the derivative of, right? So take the derivative of, okay? And I want to find the derivative with respect to x, which just means, well, we have x's in there. I want to find the derivative of u. What's that derivative?
3u squared.
Well, u is x plus 2, not y, right? So what did you say? No, well, u is a variable here, right? So let me rewrite this, okay? U is x plus 2, right? So I'm not taking the derivative of y, I'm taking the derivative of u. What's that derivative? 1, good. Okay. Well, Y is now a function of u because we don't have x's anymore, we have u's in there. So let me find the derivative of y, but since y has u's in it, we're not going to take the derivative with respect to x, we're taking the derivative with respect to u. Now, we said y was u cubed. Okay, what's the derivative of y?
Raise the second power.
Good, 3u to the second power. Good. Okay. Now, so what I've done here is I found the derivative of u, which in other words is du over dx, right? You can write the u on the outside on the top. U, and this is dy over dx. Okay. Now I love this notation. This is called Leibniz notation. Okay. And the reason this notation is very helpful is, well, if I write dy over dx, which is what I'm trying to find, right? I can write this as dy over du over dx. Aren't these two the same? Why are they the same?
Use cancel each other out eventually.
Yeah, the u's cancel each other out eventually, right? So I can rewrite this as this because the u's cancel out. Okay, well, I know what this is. I know what dy du is because I just found it. That's 3u squared. And I know what du dx is because that's 1. Okay, so that is dy du. That's du dx. Okay, now what I have is a function in term, or the derivative in terms of u. But what is u?
Raise the power, which equals one.
Not quite. What did I say in the beginning u was?
X just two.
X plus 2, right? Okay, so my derivative is 3x plus 2 squared times 1, which is just 3 times x plus 2 squared. Okay, so we'll talk about a way later on how to make this a little bit easier to do.
So I remember your substitution, but I don't remember exactly like when, how we're supposed to identify when to use it. Is this you can do with what we did at the beginning, like you can factor it out, or you can use a chain rule. But when are the ways that we're gonna like use substitution?
Yeah, that's a good situation. When we talk about an easier way to do this without the substitution itself, later on you'll learn how to do the chain rule like in your head, basically.
Yeah.
That's when we'll start talking about, okay, when can we actually figure out how to do this? It's essentially when we have a composition of functions. So we have an inside function and an outside function. That's when we deal with chain rule. I think the more examples we see, will be a little bit more clear.
Oh, yeah. You had like x squared or something, like 2x or something like that. Yes.
So you said, okay, if it's x squared times 2x, this wouldn't be
Yeah.
a composition, right? Because there's no inside and outside. But if it was 2x squared, now you have an inside and outside, right? So that's kind of where we're going with this.
Okay.
Yeah.
Because then you would be 2x.
Yeah, or for example, e to the 4x plus 1, right? There's an inside and an outside.
Right.
Yeah.
Okay. Because wait, like 2x.